Hi. Today, let's talk about the human eye. Show and tell. A little clay model of the eye. It's life size. Sometimes I can't tell if I think this is big or small. I've had so many different perspectives on eyes, seeing them magnified, seeing them in real life, seeing them in jars. Um, the, the eye is about an inch, just a hair less than an inch from front to back. Uh, This is what we're going to talk about. This is where the magic begins. Now, to get some perspective, let's take a look at this diagram. And there's something interesting about this diagram. You'll see this all the time in diagrams. And when I first was learning this, I found this so confusing. This is looking from above, or you could argue from below, but let's just say from above. And so the nose would be towards the bottom of this picture. Why isn't it just like a cross section? It's a cross section of the eye, obviously, but why isn't it looking from the side? Well, notice how I have an arrow that represents the visual axis where light goes straight through to this little white circle that's on the retina. That's where the fovea, the central vision, is. And the fovea isn't above the optic nerve, the optic disc where the optic nerve leaves the eye. It's to the side. We see that we'll see that in a minute. But first, now that we're oriented, looking down on a cross-section of the eye, light comes in through the cornea and then the lens. It's mostly focused in the cornea, fine-tuned by the lens. And then it goes through the vitreous gel, which is a gel, which means it's mostly water. But it has a consistency sort of like corn syrup. It's clear and it's kind of sticky like corn syrup. You go through that and you hit the retina. It's about 1/3 of a millimeter thick. And this is, again, about 23 millimeters, between 22 and 23 millimeters from the front of the eye, a little less than an inch. Below that is the pigmented, very highly vascular tissue, the choroid. There's a lot of blood flow in the eye. Those blood vessels that you see, the red and blue, those are not just floating in the vitreous, those are along the retina. Back to the front, let's look at the iris. We see a defect here. That's the pupil. The iris is a round muscle, and where it's open in the middle, like a donut hole, that's the pupil. Now, if we look straight, the way an eye doctor would look at your retina, and this shows what I was saying about where the fovea is, where our central vision is. That's where our vision is the most acute and clear. We see that's the fovea is the yellow arrow here, and the purple is the optic disc where the nerve fibers leave the eye to go back to the brain in your skull. Now, why do I say the brain in your skull? Because when we're looking at retina, we're looking at brain. I'll bring that up again. Now, let's have some perspective about this. What we were showing you is just a very small part of the retina. Eye doctors will also get this view. By the way, at the bottom, that's just shadows of eyelashes on this photograph. But that purple blue circle, that's where most of your central vision is, and where a lot of that previous picture was, although it includes the optic nerve head, the disc. The yellow circle is the area of the fovea. That's where most of your vision is. Look at all the area that's peripheral vision and isn't what you really center on, isn't your central vision. So we followed a ray of light. Let's back up a bit. How does that focus on the retina? Because clearly we need it to focus on the retina. And here we see what's called a ray tracing drawing. Now, let me say, there's no such thing as rays of light. You see like rays seem to come from clouds, but that's just because the clouds are breaking up the light. Light waves travel as an expanding sphere. But ray tracings are a convenient fiction. Now, one of the main points of this image is to show how this arrow is inverted on the back of the eye but just by the optics, just how you draw the geometry of it. The capital A on the right tip of the arrow is inferiorly in the small a on the image. Now, again, This could be looking down because it's also inverted left to right. It doesn't matter. It's inverted up and down, left to right. Now, I want to draw your attention to two rays, the central ones between the two rays that angle. So you see a straight line from A to small a and a straight line from B to small b. Those don't really have to be focused. They're just a straight line. You notice they don't have to be bent by the cornea of the lens. Those are in just a very small part of the bands of light coming in. That's what a pinhole does. It gets focused by limiting what you're seeing to just those rays that don't need to be particularly focused. Here we see a picture of a nautilus, a creature related to some very ancient cephalopods. And you look at its eye, and that's a pinhole eye, actually. I promised in the last talk we'd get back to this. Now, pinholes are kind of very interesting. You can wear pinhole glasses. You'll see pretty clearly, but then again, your vision is just broken up into a lot of little pinholes. People used to sell them. I don't know, maybe they still do. But there's also the camera obscura, where the rays we see here going through the pinhole. We see the same ray tracing diagram. This diagram, by the way, is an engraving from 1645. Notice that the castle on the left, the tower anyway, is inverted on the right. And we see an artist copying that picture in that room. Here we see a painting by Vermeer. And there are people who seriously think, art historians and others, who seriously think that's what Vermeer did, that part of the way he captured things was by using a camera obscura like setup. But the eye isn't a camera, not even a camera obscura. It doesn't just send an unaltered picture of the world that's out there, to the brain. Well, as I mentioned, retina is brain, but to the brain that's in your skull. What does it do? What is it doing to the image? Well, it's doing a lot, and that a lot is going on in the retina. Now, sometimes I will talk about the brain, meaning the brain in your skull, but know that that's just convenience. Every time an eye doctor looks in your eye to the back of your eye, they're looking at your brain. It's really the only time we can look at living brain tissue. Now, this is the layers of the retina. There won't be a test. You don't have to memorize these, but I want you to get a sense of the complexity. And trust me, this is a highly idealized cartoon as it is. So don't get lost in the details, but let me work through it. First, to the right, notice the light is coming from the left and has to go through several layers of tissues before it gets to the back of the retina where the light is actually registered. All the way to the right, there's the pigment epithelium. Now, the pigment epithelium is very important. It's pigmented and it does all the things we talked about before. It absorbs stray photons, stray light, so there's not as much scattering, and they don't degrade the image. But it's also a very highly important tissue. These cells help regenerate and help metabolize and keep the retinal photoreceptors, that is, the cells that receive light, healthy. Now, right to the left, that is above or towards the light from this retinal pigment epithelium, are the photoreceptors, the rods and cones that you may remember. There are somewhere between 120 and 130 million rods, mostly in the peripheral retina, and 6 to 7 million cones, mostly in the central retina, and particularly densely packed in the fovea. Now, rods are very sensitive to light. They'll see a single photon. There is no such thing as less light. As a matter of fact, it's so sensitive that it would be meaningless to have each rod send a signal. It would overwhelm your brain, your visual apparatus. So rods tend to be averaged. It'll be at least 100, maybe 400 rods, summing up an area of rods, what's being seen, to one ganglion cell. We'll get the ganglion cells later, but meaning one cell that'll send that image on. So it doesn't see clearly, but it's very sensitive. Now, cones need 100 photons, not just one, to function. And so they see best in bright light. They can be as efficient as one cone to one ganglion cell. So you're getting just 1 pixel to 1 pixel instead of 400 to 1. And that's at the most sensitive, the most visual acuity. Cones also see color, but we're going to cover color in a later talk. It's such an important topic to us. Now, the horizontal cells are the next up. And here it makes it look like, oh, they just, contact each other and a couple of other photoreceptors. And no, these can be spread out over a millimeter, which is a huge area in the eye. It could be dozens and dozens of cells it's contacting. The next up in the chain from photoreceptor is the bipolar cell. And the bipolar cells, again, will then transmit to the ganglion cell, but we can't just say it's that simple, of course. There are about 12 types of bipolar cell, by the way. Here they just show one type. And by types, they probably have slightly different functions. And so it's a very complex situation. Now, these bipolar cells not only send the impulse to the ganglion cell, which then, as you see in pink here, have these fibers that will then leave the eye and make up the optic nerve that go to the brain inside the skull. But these bipolar cells interact with the amacrine cells that you see here. Now, there are more than 30 types that we think of amacrine cells, and they also interact with each other. The amacrine cells do, and with the ganglion cells, bipolar cells. It's just feedback loop upon feedback loop, negative and positive feedbacks to craft this image that is finally going to be sent back into the skull. It's wheels within wheels. Now, this last cell type, they do show 2 different types of ganglion cells. Actually, there's probably more like 18 types, and that's really important. Now, remember, I said there were maybe about 130 million photoreceptors. Well, there's only 1.2 million or so ganglion cells that make up the nerve fibers. So you see there's a 100-to-1 ratio, and most of that's in the rods, as we said, not the cones. One last thing that's not on this image is that there is a type of ganglion cell that is actually a photoreceptor. All right, okay. It has a photoreceptor that receives light but doesn't give any vision in the sense of seeing an image. It's more like the plants or the bacteria or the algae that we mentioned in the last talk. It has to do with circadian rhythms, and yet we have those. Is that vision? Well, I called it vision. So remember, rods have poor resolution, and they predominate in the periphery. Now, peripheral vision, as I mentioned, since you're sending 400 rods to just one ganglion cell, really stinks. Outside of the blue circle, you're basically legally blind, more so as you go further away. I know it doesn't seem that way. You think you see a scene pretty clearly, but that's because you look around and you remember what's there, or you have expectations of what should be there. You fill in that scene with what you know and expect. Now, how do you know that? Why trust me? Take a look at this line of letters. But before I put them up, just go right to the last letter on your right and try really hard to move your eyes. By the way, you can't. It's literally impossible to not move your eyes at all. But you can control it partially. So just look at that last letter. It's a K. I'll give you that. Spoiler alert. And how many letters can you read without moving your eyes? You'll be lucky if you get more than 3 or 4. Maybe some can get 6. All the rest, you can't really read them. You think you can. But as soon as you let your eyes scan a little bit, you don't feel like you're looking around much, you can read those letters. Now, that's because our fovea always wants to just see what's most important. It's really for detailed vision. the people who study vision in living beings to help machines and virtual reality, robots, virtual reality, gaming, they know about this. And as a matter of fact, they use this as something called foveated rendering, where they'll have eye tracking to see where your eyes are and always make that the sharper part of the scene. Now, rods are also important for dark adaptation. This is something that the eye does. It's an eye feature. The poor vision in rods is more a feature than a bug. It's there because you don't, in the periphery and in dark scenes, you're not going to get much vision, but what you need is sensitivity. It's amazing how much light range we see every day. From the darkest night with no moon to the brightest sunlight on, let's say, on a white piece of paper as the standard, there could be as much as between a 1 in 10 million fold range in brightness. And you might say, oh, we have the pupils. Well, the pupil going from, 7 or 8 millimeters to 1 or 2 millimeters, that's only a few dozen times less area. So that isn't getting you a billion-fold or even 100-fold difference. It's really the rods doing the heavy lifting. So how do we adapt? First, in bright light, the rods and cones are both bleached. That is to say, the chemicals that actually receive the light are kind of used up. They have to be regenerated. And we do that on the move. That's one of the reasons we move our eyes, to give some a rest. But when you go to a heavy duty situation, like going from light to dark, the cones can recover first in about 5 minutes. But again, remember, they need 100 photons. They're 100 times less sensitive than rods. So you can see a bit in the dark, but it's not great. Over the next half hour, the rods regenerate. And so you adapt to the dark. Rods see more in the blue. So you're not only simply more sensitive, you're actually seeing a somewhat different scene. You're coloring it, not on purpose, but because of the wavelengths that rods are most sensitive to. Again, we'll talk more about color another time. Little fun fact, life hack, because of this, if you're dark adapted and you want to see a star that's up in the sky, look a little to the edge of it. Get a little more rods involved. So one point to make is the only time we saw actual light was in the rods and cones. You could argue maybe in that one ganglion cell. But for a visual image, rods and cones, everything after that is electrochemical signals, just nerves, just like in the nerves in your skull, in the brain in your skull. Now, next, let's go further. What else does the eye do? It processes images. It photoshops things for you. It favors edges and contrast. The ganglion cell sums up what the rest of the retina has done. It sends on impulses based on what the entire retina's feedback systems have decided are the most interesting features, based on how the light is falling and whether it seems to be an edge or there are differences. If an area is bland and there's not a lot of contrast or edges, it could be kind of compressed. It could be just summarized as, hey, this isn't interesting, let's move on. Now, no, there's really no such thing as edges. I mean, as lines, outlines in nature. There are edges, but they may be very soft. They're important to us. It's how we know there's a table there, an edge there. We won't fall off the cliff. We can go down the steps. But we artificially enhance them in our vision because they're so important to us. Now, take a look at this optical illusion. This is in part due to this kind of processing that the eye does for contrast and lines. Uh, we don't have to get into the mechanisms, and they're not really well worked out. When I read different authors, I get kind of different interpretations. But here's the real point of this. You see black dots where you're not looking. Are these black dots real? Do they have an independent existence? Of course not. They're blinking in and out just depending where you look. They're empty of a permanent inherent existence. There's no persistence at a given point in time and space. Do they exist without a brain that can be manipulated and is aware? No. They only exist because you can process them and be aware of them. They are products of our brains, including the brains of our eyes. They are, in a sense, true. You truly see them, but they are projections. They're phantoms that we project on the world of this grid. Really, we have to look around these tiny eye movements. We don't have a choice. This is nothing you can totally control. I mean, you could modify it. This helps refresh your vision. So we look at different areas slightly, keeps it interesting to your eye and therefore the image that you see. But you have very little control over it. If I came over to your house and paralyzed with an injection in your eye muscles, and you just stared, but not your vision, which is hard to do, but stared straight ahead. And there are experimental gimmicks to do this too, by really holding the eyes in place. A little bit barbaric. We won't do that. But what happens is the world disappears. That's right. The world disappears. And here's a little bit of an example, a little taste of that. With both eyes, look at that dot. Now, I know it's hard to do. You'll be amazed if you really are sensitive to it, how your eye really wants to move. And that's not just because of your thinking. It really wants to move. That's what it does. And that's what the feedback is telling it to do. But if you could just keep looking at that dot, 10, 20, maybe take 30 seconds, you're going to see a lot of these kind of interesting, neat little colored fuzzy circles disappear, or at least really fade away. And then after you see it fade, just blink or look away for a second and then look back, and they come back very vibrant. So what am I getting at? You don't see the world as it is, even at the level of the eye, let alone getting back into our brains. The only time you actually see light, and the rest is neurotransmitters and electric impulses along neural tissue, is in the photoreceptors. But anything above that photon hitting a photoreceptor, our eyes aren't just passively passing on an objective view of the world. We saw the images inverted. We don't see the periphery well. Dark is not simply dark. We adapt to it and recolor it a bit. And even in the eye, we favor variation, change. We love lines and edges. We aren't seeing what's really there, at least not completely. We are projecting on it. We are dancing with it. We're helping to create it. Now, the image the eye passes on to the brain and the skull is therefore a bit of a projection, a chimera of heuristics. What heuristics am I talking about? All the things over hundreds of millions of years of evolution that, in our case, vertebrates needed to see, needed to survive, needed to thrive. We have this illusion of conscious control. We think we ought to be able to make our eyes not move. We ought to be able to say that line, that contrast is really there. That's because you're identifying with your thinking you, the words in your head, the things you feel you have control over. That's what you think of as you, your ego. And I don't mean ego as a negative thing, just you, the thinking you that is part of how you want to control the world. Now, we inherited an eye, just like we inherited a brain, just like we inherited a body, just like we are part of a complex web of interactions going back to time before time. It's our karma. Well, let's, before we leave, talk about another product of hundreds of millions of years of evolution, our blind spot. We're looking at this picture of the retina again, and notice that where the optic nerve disc, where the ganglion cell fibers leave the eye to make the optic nerve, there's a hole in the retina. That is, there's no retina there. There's this disc, and that disc is made up of these cell processes from the ganglion cells. There's no photoreceptors there. So there's a hole. So what happens in that hole? Well, there's a blind spot that you never see. Never, ever. So look at this image of these two peppers. You close one eye and look with the other eye. So if you're looking at the red pepper, look with your right eye, close the left. And yellow pepper, look with the left eye, close the right. Hold this image maybe 3 to 4 times as far away from your eyes as the image between the two peppers is. And if you want to make your own, by the way, just do 2 crosses on a piece of paper. And again, if it's 4 inches apart, make sure you're about between 12 and 16 inches away, and just experiment. Just bring the paper or the screen back and forth. What's going to happen is the pepper will disappear. But again, you know the drill. You got to give it a little time, and you got to do your best not to move your eyes. You're going to want to look at the other pepper. Nope, look at it out of your mind's eye, out of your peripheral vision. Experiment with it. But what's really interesting is there's not a gap in your vision. What you see is the background. You see blue where there used to be a pepper. And you can make the pepper go in and out of it. You can make it disappear and reappear. Have a little fun with it. So how did we color that in? What is going on beyond the eye? Well, let's go back to the brain and the skull in our next talk.